Warning: do not try any of the things you're about to see. We are trained chemists with years of experience.
Hey, did you hear about Delta's chemistry show? Yes, let's go!
Well, welcome to our Chemistry Magic Show. This is San Joaquin Delta College, and the chemistry department, along with the student chapter of their ACS, normally puts on every fall a Chemistry Magic Show. This time, because of this thing, we have to do it virtually. So my name is Dr. Kim. I'm usually the person emceeing it, and we just want to welcome you to this. One of the things you will see, which is very important when you're doing any chemistry, is you need to have safety. First things first, goggles. Second thing, your gloves. So whenever we're doing or practicing any safety in the lab, we always make sure we have to have our proper safety protection on. And we hope you enjoy the show.
Like to in hot water. I love this demo.
3, 2, 1.
Well, hey, so the demonstration you just saw was actually the decomposition of hydrogen peroxide, and it creates a thing we call elephant toothpaste. In this example, we have Dr. Mary Ellison doing the same exact reaction. You'll see that she has a glove on to protect her hands from the heat that's actually generated, since it's so exothermic. And you can see the steam rising and the actual water vapor coming out of the flask. So we're showing you a lot of exothermic reactions and fire. And so we're going to have Dr. Reedy show us a couple more exothermic reactions. And enjoy.
This Pringles can has a hole in the plastic end which will allow air into the can, and there's a small hole in the metal end which will allow hydrogen out of the can. And you're going to see why that's important in just a moment. So let me put on my safety glasses and we'll go ahead and fill our Pringles can with hydrogen. So our can is now completely filled with highly explosive hydrogen gas. I'm going to put on my hearing protection and then let's light it. So we'll peel off the tape and very carefully light the can. Oh, that was not very exciting, was it? You need hydrogen and oxygen in order for this reaction to occur efficiently. Now, as the hydrogen leaks out the top of the can and burns in air, air is moving into the bottom of the can. And the oxygen and hydrogen are slowly mixing together, and they're eventually going to reach that perfect 2-to-1 ratio. When they do, the can's going to make a whining noise, and that tells us in about 15 seconds, boom. And there. Five, 4, 3, 2, 1. You can feel that in your chest.
A little bit of a costume change, but the next demonstration we're showing you is called chemical flares, and it uses a similar reaction that we might see later on with the flaming gummy bear. But where you can see this a lot of times is in fireworks, and what we're doing is we're actually exciting different metals, and when they excite, the electrons that are composed in that actual metal get excited. When they relax, they give off different colors of light. And that's what you're seeing here.
And I I start to pull my long nylon rope out of that huge mixture, a long, continuous molecule, which then can be refined into those famous Joe Namath nylon stockings.
In this graduated cylinder, we have deionized water with a little bit of sodium hydroxide to make the solution basic. So let's go ahead and add our universal indicator, which changes lots of different pretty colors depending on the pH. So right now our pH is on the basic side from our sodium hydroxide. Now to this we're going to add some dry ice. Dry ice is basically just solid carbon dioxide, and when dry ice dissolves in water it forms carbonic acid, which is slowly going to lower the pH, and we should see a series of color changes. So let's go ahead and add a few drops of hydrochloric acid and see if we can push the color a little further. Okay, a little bit of that. Now we've got more of an amber color. A little bit more. Got it sort of orange, and if we put enough in there, there we go. We can push it all the way to red.
1, 2, 3.
Well, welcome to one of our last demonstrations here. We are going to be using something called liquid nitrogen. Liquid nitrogen is extremely cold. It's about 77 Kelvin. And it's basically where you take in nitrogen, which is about 78% of our atmosphere, and you liquefy it. As we all know, nitrogen is in the air, like we just said, and it doesn't really want to be liquefied. In order to do that, we have to cool it off by a lot. 77 Kelvin is extremely cold. It's about negative 322 degrees Fahrenheit. That's how cold this is. So I'm going to show you what it looks like. I'm going to wear some safety gloves here and also my eye protection. And we'll play with it a little bit, do some demonstrations, and show you how cold this stuff really is. So these two containers are special containers that can isolate, not fully, but a little bit, the liquid nitrogen from the outside atmosphere. And so they're called Dewar flasks. So behind here, I have another Dewar of liquid nitrogen. And we can see it's actually, that white is actually a cloud. It's actually the water in the air being cooled off so much to form a cloud. You can actually see it boiling, the liquid nitrogen boiling in this Dewar flask. As it cools off, we'll see it actually stabilizes and ends up becoming, looks more like a liquid. So we can cool things off really quickly. So for example, we can cool off flowers really, really quickly. So here's a flower that we have. We'll trim it a little bit. So a normal, nice looking flower, when we cool this off really quickly, it freezes. It basically freezes everything in here really quickly. It pretty much looks the same, but it becomes extremely brittle due to the fact that all of the moisture in there, all the water, essentially froze almost instantaneously. We can do the same thing we'll do with a balloon. So for example, we can see here's a balloon. This is filled with normal air. I just pumped it up. And we can cool this off, and we can see the balloon. This also has some nitrogen, liquid nitrogen in it. Will actually deflate. I'm going to push it down here a little bit so that it fully deflates. We can actually do a little bit more magic than just that. Whoops. stuck. And when it fully deflates, it actually changes color. As we can see, all of the air that was in there now is able to warm back up and re-expand where we had cooled it off before. It actually didn't do any magic. I just had another one in there. There's the original balloon. And you can see it re-expanding again. All of the air molecules that were in there got so close together because they cooled off so much that it causes that balloon to actually shrink. No. You can see that. We can also, since this likes to, liquid nitrogen likes to rather be a gas than a liquid, we can actually use that effect to pressurize a small bottle. And when we do that, we can cause a kind of a fountain effect. Kind of like if you had a juice box and you blow into the juice box and all the juice comes out, kind of the same trick. So we'll use a little bit of a funnel here. We'll pour some of this in here. Kind of hard to pour in there because it kind of tends to bounce all over the place like that. We got some in there, and then causing the same effect, we can actually see what we call the liquid nitrogen fountain. Pretty neat. We can also take objects like a regular racquetball, extremely bouncy, and we can cause all the molecules in here to become very, very close together, cool them off really like quite a bit. We'll put that in there, drop it in there, we'll cool it off. And we'll see, no longer very bouncy, you can actually break it. So this is liquid nitrogen, except like we said, it's extremely cold, very, 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 very cold stuff. So thank you for watching our virtual chemistry show. If you have any questions at all, feel free to contact the chemistry department here at San Joaquin Delta College, or even the student chapter of the ACS here at Delta, and we can try to answer as many questions as we can get. We thank you for watching again, and we hope you enjoyed it.